This lesson is on integration by substitution, which is integrating composite functions, or basically anti-deriving chain rule type problems. We would use a chain rule to derive a composite function, so this is the opposite of the chain rule. Integrating by substitution, anti-deriving composite functions, the reverse chain rule. So, you get your notation for your integral. The integral of f of g of x times g prime of x d of x with respect to x, or dx, not d of x. So basically, you remember with your chain rule, you had an outside function, you had an inside function. You would take the derivative of the big function, keeping the inside function the same, and then multiply by the derivative of that inside function, of the little function. So you see, here's your inside function, g of x. So you have f of g of x, some big function with g of x inside, with a little function inside, times the derivative of that little function. So when we anti-derive this, the derivative of the inside function is going to go away because we're anti-deriving. We're getting rid of that times by the derivative of what's inside. So the antiderivative of this composite function is going to be capital F, the antiderivative of the big function, of g of x, leaving the inside function the same. When you derive the outside function, you left the inside function the same. When you anti-derive the outside function, you leave the inside function the same. Plus c. Nothing changes here. There could always be a constant at the end. Trig, composite functions, power functions, whatever. Any antiderivative, general antiderivative, indefinite integral, can have a constant at the end. Now what we're going to do here is we're going to use what's called u substitution to make it a little bit simpler, a little bit easy to see what you're doing. So we're going to let u equal g of x. We're going to let u equal the inside function. So instead of f of g of x, you have f of u with respect to u. Because du is going to equal g prime of x dx. Du is going to equal the derivative of that inside function with respect to x. So if I plug in u for g of x, I have f of u. If I let the derivative of u be g prime of x dx, g prime of x dx, this whole thing is du. So now I get the integral of f of u with respect to u. And that would equal capital F of u plus c. We're going to do several examples here to help you see where this is going. We're going to start off with the easiest kind, the kind that you like to see, to kind of work out real nice. And then we'll work our way to the hardest kind, which aren't even that bad. We're just going to progress slowly through them. So you have the integral of x squared plus 1 squared, 2x with respect to x. So we have something squared. So we know that something squared is going to be our big function. So we're going to let u equal what's being squared. So u is going to equal x squared plus 1. Now, once you know what you, or once you've decided what u is going to be, then you write u equals x squared plus 1. Then forget about this for a minute. Take u and derive it with respect to x. So du equals 2x dx. So you derive this. Don't look over here for what you're trying to find. Derive this like you normally would, like this is the only thing in front of you. Du equals 2x dx. Now you want to rewrite the integral in terms of u. So I'm going to rewrite the integral in terms of u. Let me get a pen here. So u equals x squared plus 1, so I'm going to have the integral of u squared. So I have u squared. So that's gone. So I've used u substitution to rewrite this part. Now I'm left with 2x dx. I look over at my du. Du equals 2x dx, that exact same thing. So I can replace 2x dx with du. So now that's gone. I've now rewritten the entire integral. I've accounted for everything in there. Now I can go ahead and anti-derive this. Now you go back and pretend like this was just what you were given. Forget about all this and other stuff. You're done with that until the very end. The integral of u squared du, that's just a power function. Add a power, divide by the power. So the integral of u squared du is going to be u cubed over 3. And then again, plus your constant integration, plus c. Last step, once you have that 1/3 u cubed or u cubed over 3 plus c, your last step is to back substitute. Because remember, we wanted this integral with respect to x, this antiderivative with respect to x. So I replaced the u with what I started with. 1/3 x cubed plus 1 cubed, x squared plus 1 cubed plus c. So I back substituted after I did my u substitution. And a real quick check, if we derive this, it'd be 3 times 1/3 would leave us with 1. X squared plus 1 to the second power. Constant goes away. Times the derivative of what's inside, which is a 2x. X squared plus 1, 2x. X squared plus 1 squared times 2x is what we have here. Next, a trig function. There's going to be two types of trig functions that you see usually. One, where you're going to have the sine or cosine or whatever of an angle that's not just x or theta. And other types where you're going to have combinations or things, cosine or trig functions raised to a power. The first one's the simpler type, where the integral of 5 cosine of 5x dx. Well, in this case, if you just see an angle, if you just see one trig function, you're probably going to let u equal the angle. You're going to probably use your substitution where u is the angle. So u is going to equal 5x. Now again, forget this back here. Once you make your substitution, derive the u term, the u equation. Derivative of u equals 5 times dx. Now you have u, you have du, now you go back and substitute. U was 5x, so I'm going to write cosine of u. Cosine of u. That covers that part. Now I have a 5 dx left. Du equals 5 dx, so this works out nicely. 5 dx is the same as du, so I plug in a du. Those parts both go, so I'm left with cosine of u du. Now you integrate that, forgetting about all this other stuff, and then just integrate it. This was the problem you were given. Once you substitute, forget the original problem for a minute, and integrate what you have here. Like this is what was given to you from the start. The antiderivative of cosine is sine. Angle stays the same, so sine of u. Again, add your constant of integration. And then you remember the last step, back substitute. Go back and plug in u anywhere you see a u. So you get sine of 5x plus c. Now, here's an example where you must adjust du. This is the second type of example, kind of like the second tier, where you got to do a little bit more in order to find this indefinite integral. But if you follow these steps, if you listen to what I say, it shouldn't be that bad. It shouldn't be bad at all, actually. So again, integral of x squared plus 1 squared dx. Well, something being squared, that's going to be your big outside function. Something raised to a power is almost always going to be your outside function. So we're going to let u equal this little function on the inside. U equals x squared plus 1. Now, again, forget about this. U equals x squared plus 1. Du equals 2x with respect to x. 2x dx. Now you have u and you have du. Now you go back and substitute. So I'm going to write this in here first. The integral of u was this thing, so I'm going to have u squared. Takes care of that. I'm left with x dx. I want to replace x dx with something equal to x dx. Du is equal to 2x dx. That's not exact. I've got to make this part look exactly like what's left. I have a 2x dx, so I've got to get rid of that 2. So if I divide both sides by 2, now 1/2 du is equal to x dx. So now I can substitute. X dx is what I'm left with here. That's equal to 1/2 du, so I have to plug in a 1/2 du here. I like to put my 1/2 out front. And there you go. There's your indefinite integral in terms of u. Much easier than looking at this. Now again, just a general power rule. Add of power divided by the power. So I go to u cubed divided by 3. So the integral of 1/2 u squared du is 1/2 u cubed divided by 3 plus c. Now I'm going to kind of go combine these two quick steps. I'm going to combine the fractions, and I'm going to back substitute. So 1/2 times 1/3 is 1/6. U was x squared plus 1, so I write x squared plus 1 cubed plus c. Key in these type of problems is you want to do your u substitution, u squared, find out what's left, and make du look exactly like that. So you might have to move things on this side, so you're plugging in things in terms of u. Okay? Here's those type of trig integrals where you're not going to have u as the angle. I have a sine squared, I have a cosine. So I have two trig integrals, or two trig functions in here. Now, this kind of works out nice. Sometimes with trig functions, if you see a secant squared and a tan in there, well, you let u equal tan the derivative of secant squared, or u equal secant the derivative of sec tan. There's a couple options. Here, you have one thing squared and a cosine, sine squared and a cosine. Well, derivative of sine is cosine, derivative of cosine is negative sine, so they're kind of derivatives of each other, the exception of their sign. That's simple to fix. But one of these is squared, is raised to a power. In that case, you're going to want to let u equal whatever's being raised to a power. So I have sine squared of 3x. I'm going to let u be what's being squared. So u is going to equal sine of 3x. Because that's what's being raised to a power, raising sine of 3x to the second power. So u is going to equal sine of 3x. Now again, forget this. Derive your u substitution equation. du equals cosine of 3x times derivative of the angle, so 3 cosine of 3x dx. Now go back and substitute. Sine squared of 3x is the same as u squared. So that's gone. You're left with cosine of 3x dx. You have du is equal to 3 cosine of 3x dx. So you want to divide both sides by 3 again, very similar to the last problem. So 1/3 du equals cosine 3x dx. Now this is exactly what's left. Cosine 3x dx, cosine 3x dx. So this part is what goes in. So you get 1/3 u squared from here, du. Now again, anti-derive using the power rule. Add a power, divide by the power. So u squared goes to u cubed over 3. 1/3 times u cubed over 3 plus your constant of integration. Combine your fractions, back substitute, you get 1/9 sine cubed of 3x plus c. Okay, now we're going to do a definite integral with substitution. There are two ways to do definite integrals with substitution. I'm going to show you both here. I don't think one's really too much easier than the other in most cases, but I want to give you a couple options, what you prefer to do, but you do need to be familiar with both. So you're going to start with the definite integral from 0 to 1 of x times x squared plus 1 cubed with respect to x. So find the area under this curve between 0 and 1. So you're going to get a value. The definite integral gives you a value. In order to do that, we can't anti-derive this yet. So we're going to use u substitution. You have an x and you have something cubed. So u is going to be that inside function, whatever's being raised to the power. So u is going to equal x squared plus 1. Again, forget about this. Derive this with respect to x. du equals 2x dx. Then you do your integration, your substitution. You're going to start with u cubed. So I have u cubed here. That's taken care of. X dx. 2x dx, I'm going to need a 1/2 du. Divide both sides by 2. So I get a 1/2 u cubed du. From 0 to 1, 1/2 u cubed du. I get a 1/2 u to the 4th over 4. So I get 1/8 x squared plus 1 to the 4th from 1 to 0. You plug in 1, you get 2 to the 4th, 2, 4, 8, 16 over 8 is 2. So I get 2 when I plug in 1 for this value. 0 plus 1 is 1 to the 4th is 1. 1/8 times 1 is 1/8. So 2 minus 1/8 is 16/8 minus 1/8 is 15/8. Now here's another option. In this case, it doesn't save you too much time. In some cases, it will save you a little time, so I do want everybody to be familiar with this. Instead of going through using U substitution and back substituting your exit terms and then plugging in your values, you can switch your limits of integration. In terms of x, I was going, or the function was going between 0 and 1. If you turn this over into a function in terms of u, well, x was 0, so 0 squared plus 1, u would be 1. So my lower limit, instead of being 0, would be 1 if I want to stay in terms of u the whole way. My upper limit was 1 when I was talking about x's. 1 squared plus 1 is 2. So I'm going to go from 1 to 2 instead of from 0 to 1. So I changed my limits because I figure instead of going all the way through and then back substituting and plugging in again, I can just stick with u's. Because you're not looking for an equation, a function, an antiderivative, you're looking for the value of the area under the curve. So as long as your substitution is consistent and correct, you'll get the same value. We'll go through it real quick. You still get 1/8 u to the 4th. Well now, I plug in 2, 2, 4, 8, 16. So 16 over 8 is still 2. So when I plug this in, I get 2. 1 to the 4th times 1/8 is 1/8, so I still get the 15/8. The more complicated the u, the more this will help you. The more complicated your original thing you're substituting, the more this will help you clear up and go through the math a little easier. Now here's an example where you have to use u a couple times. All right, this is kind of like the third tier, the trickiest type you could ever see in a Calc 1 U substitution type of problem. This is not extremely tricky, but this is as hard as it gets. So if you understand this, you're in real good shape for this section. So I get the integral of x radical 2x minus 1 dx. Obviously, I have something under a radical. That's going to be my little function. U is 2x minus 1. Derive. du equals 2 dx. Now you substitute. So you're going to get u to the 1/2. So I'm going to have the integral of u to the 1/2. That takes care of this. Cross it off both ways so you don't get confused. Now I'm left with an x dx. Well, du is 2 dx. There's no x in there. And you can't add an x or multiply by an x because I'm going to have u's and x's, and that's no good. So I'll just solve for dx. I'll get rid of this dx, which is 1/2 du. So now I'm going to have a 1/2 and a du. So now dx has been substituted for. But now I have an x in there. I have to turn that into something with a u. So I'm going to use my u equals 2x minus 1. And I'm going to solve that for x. Add 1, divide by 2, so I get x is u plus 1 over 2. So that's going to be my substitution. Now you're going to have to use a little algebra to clean this up. You see that here, 1/2, u to the 1/2, u plus 1 over 2. So, 1/2 u to the 1/2 times u over 2. Well, the 2 is going to make this a 4 on the bottom. U to the 1/2 times u to the first. Add the powers, I get u to the 3/2. Now splitting this into u over 2 plus 1 over 2, I do 1/2 u to the 1/2 times 1/2. The 2's still making a 4 on the bottom. U to the 1/2 times 1 is u to the 1/2. So this is now my indefinite integral. The integral of 1/4 u to the 3/2 plus 1/4 u to the 1/2 with respect to u. So the only difference here was I had an x I couldn't account for, so I used my original u, solved for that, still substituted everything in terms of u, did a little bit of algebra to simplify this into something u to a power, something u to a power. Remember the power rule, we want something variable to a power always. And now I can anti-derive. Add a power, divide by power, add a power, divide by power. So I go to up to 5/2 multiplied by 2/5. So I get 1/4 times 2/5, u to the 5/2. Up to 3/2 multiplied by 2/3, 1/4 times 2/3, u to the 3/2 plus c. Again, I'm going to simplify everything and back substitute in the same step. 1/4 times 2/5 is 2/20ths or 1/10. U to the 5/2, so 2x minus 1 to the 5/2. Plus 2 over 12 is 1/6. U to the 3/2 or 2x minus 1 to the 3/2 plus c. And that's it. That's the worst you could possibly see, where you end up with an x that you can't account for, and you got to just solve this for x and use u twice. So I used u here, and I used u to solve for x and used it there. A little bit more algebra, but if you take your time and stay organized, shouldn't be a problem. You get everything in the power, anti-derive, and here's your indefinite integral.